Welcome, and we're going to do a demo today that's going to expand on our knowledge of regular expressions in finite state machines. So the first thing we're going to do is we're going to play around with how to match regular expressions in Python using the Python RE library that you can see here that I've imported. And then what we're going to do is we're going to play around with cellular automata and implement Conway's game of life that we have talked about in the lecture. So let's get started. So first of all, what we're going to do is I've got a comment here that shows some example strings that are only using the absolute base regular expression syntax. So we'll try, first of all, to create some code that matches just using this syntax. So let's first of all try this out. So in order to use regular expression matching in Python, you need to import the RE package, which I've already done, as you can see. And then you need to compile a regular expression. Now, compile, what does that mean? It's not a computer program. Well, compile actually means to turn the regular expression into a finite state machine. So you can implement a finite state machine. You can probably imagine, based on what we've seen in the previous, in the lecture, because you've seen that the finite state machine is really just a matter of you're in a current state. What input did you see? And then that tells you which state you go to. So it's just a matter of if statements. So it's relatively easy to implement in code. And so this compile function that I'm going to show you, it takes a regular expression and turns it into code that matches a finite state machine. Okay, so let's actually try this. So let's choose one of these, maybe this one right here, this 4-digit binary number here, but the less optimized version. And so we'll call this 4-digit binary, and we'll do re.compile. And then in quotes, I'm going to paste that regular expression. Okay, so that regular expression is just using the basic syntax. And I'm going to want to try to match this regular expression. So let's just do that. So I'm going to say, let's call this 4-digit binary match, let's say. And then I'll just say 4-digit binary dot match, and then we'll pass it a string. So this string is going to be a potential binary string. So let's go with the 1001. That's a 4-digit binary number. Next thing I'm going to do, now remember, one thing I forgot to mention is that the match function is going to look for the occurrence starting at the beginning of the string. But it doesn't actually care if there's some extra junk afterwards. So if we want to eliminate that, one thing that we can do is we can make sure that it starts at the beginning of the string, which isn't really necessary in this case, putting in the caret symbol, kind of the up arrow symbol, at the very beginning. That means that the first digit of the binary number needs to be right after the beginning of the string. So it has to be the first character in the string. And very similarly, you can have $sign at the end, which says that the last or the fourth character in the binary number has to be just before the end of the string. In other words, it has to be the last character. That is helpful if you want to make sure that the input only matches a binary number. There's no extra stuff at the beginning or at the end. And you can use either one of these. You don't have to use them both. But here, in this case, I want to make sure there's no extra stuff at the beginning and there's no extra stuff at the end. Now, match is also only going to find one occurrence of this regular expression match inside the string. So looks like 1001 should match, so that should be okay. If there is no match, FTP match, then it returns none. So you can actually do if FTP match, because that's going to not pass if there's no match. So then what I'm going to do is we'll just do a print, and then let's just say something like found a 4-digit binary num. And then what we'll do is we'll do FTP match dot group. Okay. Now group is actually a little bit more powerful function. Actually, you can see since the autocomplete here, it has a couple different versions where you can pass it which group you want. You can actually get individual parts of the string that matched according to your regular expression. It's a little bit more of an advanced topic, so we'll just execute group without any arguments at all, and that'll give us the full matching string. Okay, so let's see if that works. So you can see, hey, look, it found a 4-digit binary number, 1001. Here we go. Okay. All right, so that is not a very efficient way to find a 4-digit binary number. So what I'm going to do is, let's actually just duplicate this code to save us a little bit of typing. And then what we'll do is we will optimize the regular expression to match 4 binary digits. So one way that we can make it simpler is by doing 0 or 1. Remember, this part of the regular expression here is just 0 or 1. The vertical bar just means or. And then the round brackets around it just is to group the 0 and the 1, 0 or 1, together as a single term. So this is 1, 0 or 1, then another 0 or 1, then another 0 or 1, then another 1. So there's 4 of them. But we could actually just put curly bracket 4 after that, and that'll make it appear exactly 4 times. But with the extensions, there is a way that we can make this even more efficient, because 0 or 1, we can use square brackets for that. So we can literally just put all the characters that we want to match. It'll match any one character in the square brackets. Since only a 0 or 1 are in the square brackets, that's going to match a 0 or 1. And then if we follow that up with curly bracket 4, then this will match exactly 4-digit binary number. So let's see if this matches as well. And it looks like both of them do work the same way. Clearly this one is simpler, or at least easier to type. But anyway, that's how that works. So you can see that the extension symbols can make the regular expressions much more efficient. All right, so let's come up with a language that we want to match, and then we can come up with a regular expression that will correspond to that language. So let's say, for example, I want to match some optional A's at the beginning of the language. So let's say, for example, let's come up with just some examples. Some optional A's at the beginning. So let's say there are 3 A's. And then at least 1 B. So let's make it exactly 1 B. And then at least 2 C's at the end. Let's make it exactly 2 C's. So in this one, we have some optional A's, which means we could have 0 A's. And then we have at least 1 B, so we could have 2 B's, and at least 2 C's, so we could have 3 C's. That would also match. And we could have 2 A's and 1 B and 4 C's. That would match as well. We could have 1 A, 2 B's, and 2 C's. That would match as well. So these are all examples of strings that should match our language. So a regular expression for this, well, let's first figure it out. Let's call this the ABC language. And we'll just say re.compile. And so because the A's are optional, but I can have multiple A's, we're going to use A star. So remember, we're going to use the closure operator for that. We don't need any brackets here because A is just a single symbol. We usually use brackets if we're going to have like alternatives. There's no need in this case. Then in the case of B, we had to have at least 1 B, so there is a symbol already for that, B plus, and that's just a 1 or more closure. So that means that there has to be at least a B. And then at the end, we had at least 2 C's. So there is actually a notation for this. It looks like this. We do C, and then what we do is we do 2 comma, and then it says, okay, we can match 2 or more C's. That's actually not any more efficient. So I probably would be inclined to do it this way. I'd do C, which literally just matches a C. There has to be at least that 1 C. And then C plus means that there has to be at least 1 more C. So a total of 2 or more C's. So let's give this a try. So we'll just do ABC match is equal to abc.match. And then what we're going to do is we're going to put one of these in there. I don't know, let's pick this one. And some quotes. Just say if ABC match. By the way, you can do this if you want to. Not equals none. Then you can say I found an ABC string, not really ABC obviously, but for lack of a better term, I'm going to say ABC string. I'm going to say ABC match.group to figure out what it was that actually got matched. And I could put an else clause in here and say, well, I didn't find anything. But let's see what this has got. So you can see anyway that it matched the entire string. But we didn't put any of those special symbols, the caret or the $sign in there to make sure that it worked that way. So this is actually an opportunity to experiment with the other way we might want to match. So up here, we're trying to match a 4-digit binary number. I can't imagine why somebody would want that maybe on like a computer science test. And it might say, well, what is the number 7 in binary or whatever? And then you have to type in the binary number. And I might verify that it's actually a binary number on like a website or something. And so something that the user typed, the whole thing needs to match a certain pattern. More realistically, you might look for something that matches a phone number or an email address or a URL or whatever. So in those cases, then you want it to match the entire string, and as a result, you would normally put the caret and the $sign in the regular expression like we've done here. Other times, you might want to find something that matches the pattern within the string. And so, for example, I might have something like this. So we could put something like this, and then he said, and then this in a weird thing in quotes, really loudly. I don't know what the heck that means. But anyway, when we run this now, these are all just characters here. Oops, I forgot I used match. And this is actually perfectly fine what I've got here, but the fact that I'm using match means that it has to start right at the beginning. If I want to search within a string, I have to use the search function. So if I type in search now, it looks within the string and it finds a match. Okay. And this is going to probably come up again a little bit later, but I will just point out that the recognizer for these regular expressions is going to try to greedily match. It means it's going to try to match as many characters as possible. So you can see here that we've got CC plus at the end, which technically just the C and the C would match. But it does grab these extra C's because they are also valid characters within the string. So it tries to grab as many characters as it can. And so in the case of the A star, it takes as many A's as it can possibly get, and then it gets to the B, and it tries to grab as many B's as it can get, and then it tries to get all of the C's. Okay, so even though technically this match, it could just match ABCC, for example, that would be a perfectly valid string according to this regular expression as well. And it's within the string, so it could find that. It actually found AA, B, C, 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 C instead. So it's called a greedy match. It tries to just maximize the number of characters that are part of the match. All right. So those are kind of toy languages. So maybe let's do one that's a little bit more realistic. Let's try to do a phone number. So we'll just do re.compile. And what we're going to have is a phone number is going to be, let's say, for example, we're going to have, let's actually come up with a couple of example phone numbers before we start. So for example, we could have a 1 dash and then something like a 905. Let's put in the university phone number. Okay, so there we go, 905. And we could also just have just the area code and the phone number. And then we could also, even though we don't typically use phone numbers without the area code anymore, some people will share their phone number this way, particularly for like landlines and stuff, because it's kind of implied what the area code might be. So if we want to match a phone number like this, it could get a little bit complicated. So maybe let's just start by matching this part of the phone number, and then we'll add on the other two bits as we get to it. So we're going to be looking for a phone number. Let's look for one within a string. So if we're looking through email messages and I'm writing Gmail or some other mail app and I want to find phone numbers within it, I might want to highlight it so that I could place a call or add it to my contacts list or something like that if I find a valid phone number within an email message. It wouldn't necessarily be kind of on its own line. All right, so basically what we want to do is we want to find some digit characters. So digit characters are easy. You can do a \d for a digit character, or you can do in square brackets 0 through 9. I kind of like the 0 through 9, even though it's not quite as efficient. So let's use that. And we want 3 of those. So I'm going to use curly bracket 3. And then we're going to have a dash character, and then 4 more digits. So we're going to have 0 through 9 again, curly bracket 4. All right, so this should actually match that phone number right there. So let's give that a test. Oops. First of all, I should search. So I'm going to do phone.search. I'm going to use that phone number. I'm just going to look now if the phone match. And that's just going to be phone match group, dot group. Okay, let's give this a quick run just to make sure it matches okay. Looks like it does. That's good. But if I actually have something like 905-7218668, it's going to find it, but it's only going to find just the 7218668 part, because we didn't tell it that it could possibly have an area code at the beginning. And if we start matching right here, you might say, well, this is the first 3 numbers. These are the first 3 digits here, and then a dash. That seems to match so far. And then we find some more digits, but it requires that there's 4 digits, and we don't have 4 digits. So when we get to this dash character, the regular expression, or really the finite state machine that it compiles to, is going to say, whoa, okay, that doesn't look like it matches. So then it's going to keep on searching. So when it starts searching, it'll start searching starting at the 0, starting at the 5, starting at the dash. When it starts searching here, then it will find a match. And that's why we ended up getting a match here. But let's add to the beginning an optional area code. So I'm going to put the whole thing in round brackets, okay? And I'm going to put a question mark there, because a question mark, kind of like the closures, it says that I want either 0 or 1 instance of what's in those brackets. So in this case, I'm going to have, I really want to do \d because I didn't use \d, but I also kind of don't want to mix and match. So I'll use 3 digits and then a dash. So notice that the dash is also inside the brackets, because I don't want the dash if there aren't 3 digits of an area code. So we'll save that. You can see here now, within that string, it matches the whole thing. And I could put some more text in there, but you've seen an example of that up here, so I bet you won't be too surprised if that were to work. And you can nest this sort of thing. So for example, I could have the 1 dash, but I don't want the 1 dash if I don't have an area code, because at least I don't think you can dial a phone number that way with 1 dash and then just the 7-digit phone number. So what I'm going to do is inside here, I'm going to have another optional expression. And I'm going to have 1 dash in that. Now, it has to be a 1, so there's no other options. Just a 1 and then a dash, and that part is optional. So I'm going to change this phone number here to a 1 dash. And before I made that change, it still would have matched the 905-7218668 part. But now you can see that it also grabs this. And if I take out the 1, it should still match. Oops, because I made it optional. Yeah, still matches. It only matches, obviously, this part of the regular expression, because within this part is optional here. So if we don't have that, and then we jump right into 3 digits with a dash, then it assumes that's part of the area code. And you notice that this is actually a more complicated problem than you might think if you think about the way that this works. And you might think it's very easy to recognize a pattern like this. But if you think about it, this 1 is also a digit between 0 and 9. So when I encounter that 1, is this like going to be a character 1 specifically the country code? Or is it going to be 1 in the area code, or a 1 in the 7-digit part of the phone number, the exchange part? It isn't known, actually, and so it has to try all those possibilities. First, it tries to evaluate to see if it's a 1 dash. If it isn't, it might need to backtrack and say, okay, well, maybe that 1 was part of the phone number. Just to show you, I'll change this to a 1 so that we would actually have a 1. It would start to match this part of the expression. You can see here that it still manages to figure out that that 1 wasn't part of the country code, it was part of the area code. I'm going to change it back to a 9 anyway. Okay. Let's do one more. Why not? So an email address is notoriously complicated. There's underscores and all that stuff. So I'm going to leave that one as a really advanced one. You could do a subset of email addresses, which is actually a really good exercise. But what we're going to do is we are going to do names. So we'll make a regular expression to match a full name. So what we're going to do, I'm going to assume that the names there are obviously some exceptions where people will have, separated by spaces, they will have words in their name that are not capitalized. So for example, somebody might have Vaughn in their name, and they don't normally capitalize Vaughn. So I'm going to keep things simple and just say that we're only going to recognize names that have a capital letter followed by, let's say, at least one lowercase letter. They're separated by spaces. There definitely are, hyphenated names and stuff. But just to keep this not too complicated, let's not pay attention to that. So this might be something where somebody types in their name on a form. So what we're going to do is we're going to include the caret at the beginning and the $ at the end. So I'm going to have the very beginning of the name has to have a capital letter. Okay, so I'm going to say it has to be A through Z. And then we have to have a lowercase letter. It's not an option, uppercase or lowercase. In fact, we can have one or more of those lowercase letters. Okay, so for example, the name she, XI, would be a good match here. So we would have a capital X and a lowercase I. That's 1, it just needs to be 1 or more. That would work perfectly fine. Okay, so there we go. This will match a single name. Let's try this. So we'll say full name match is equal to full name. And this one, we're going to use match instead of search. And let's search for James. Okay. We'll just print out the results as always. Now, it's not a full name yet, but I'm eventually going to change the regular expression so it matches a full name. So we're just going to say fnmatch.group here. I don't know if you can hear my cat's feeder has a little recorded message. Okay. So anyway, you can see that that matches. It matches James. Here's what I want to do. I want to match a full name. And obviously things get complicated because we could have people without middle names. And we could have people with more than 3 names. But just to keep things nice and simple, what we're going to do is we're going to have 3 names exactly. Okay? And this part of the regular expression right here already matches a name. So I'm just going to copy that. That matches a name, and then we're going to have a space after. Let's accept any kind of space, so we can use \s so that matches a space or a new line or a tab. Probably going to have spaces in between, but just to keep things simple, we'll put \s so that it also matches if we have tabs in between the name, let's say. So there we go. So this allows us to have a name followed by a space. So an uppercase letter, 1 or more lowercase letters, and a single space character. It could be a space or a tab or a new line. All right, I'm going to actually have exactly 2 of those. And then we're going to have that same string again without the space. So now we're going to have 3 total names. Okay, so let's just go through this again. 2 capital letters followed by 1 or more lowercase letters followed by a space or some other kind of white space character. And then a capital letter followed by 1 or more lowercase letters without a space. So that should match there. If I just did 3 here, it would mostly work, but I'd need to have a space afterwards, and that space would count as part of the match. Not the end of the world, but this is a little bit more precise. Okay, so there we go. You can see now that it found a full name. So that's pretty nice. All right, so that's it for the regular expression content. What I want to do now is something a little bit more fun. I want to create Conway's Game of Life. And actually, if you look up Conway's Game of Life, there is a website. I'll share a link to it down in the description where you can just basically draw in the states for the various cells and try it out yourself without writing any of this code. But I thought it would be good to experiment and learn a little bit about how the code is implemented. So because this is kind of a long bit of code, and there's some stuff related to drawing, I have written some of the code already. So I'm using the curses library, and the curses library is a way for you to kind of draw graphics but using text. So it's going to basically use blocks. So it's going to draw squares in place of the graphics for our Game of Life. But that works out fine because the way you implement the squares in the Game of Life is the way you implement the graphics is usually in blocks. So it's kind of the perfect case for it. And the ncurses library is designed specifically to create graphics, but on the console. It's a little bit trickier to implement install in Windows. So even though I'm using Windows here, I already have a Linux command prompt down here. And so I'm basically ready to go. Just put myself in the proper directory, and it's ready to go when I want to execute it. So this is me using the Windows subsystem for Linux version 2, and it allows me to run my Python programs. And I've just CD'd to the folder where this particular file is found. It's on my D drive, and there's the folder for it. So you can always access your Windows files in Linux, and also vice versa. With the newest version of WSL. So I've already got some program, a function here that's going to draw the current state of the world. So I'm going to have basically a two-dimensional array that's going to keep track of what the state is. If you remember with the Game of Life, every single cell in the grid has a state of either alive or dead. Okay, and so draw is basically just going to draw a white block if that particular cell is alive, and it's going to not draw a block if it's dead. So it's going to draw a space if it's dead and a block if it's not. So that's basically how that works. Okay, the block is just basically a space but with a white background. So that's how that works. There's also a function called is this a valid coordinate? This is going to help me in my program so I don't accidentally try to draw something at a location that's invalid. I don't try to check to see if it's a valid neighbor. So I've already implemented this, and it just checks to make sure it's within sensible boundaries. This is just using like a big complicated Boolean expression, but if you prefer, you could use a big if statement like this that does exactly the same thing. It just returns the result of this Boolean expression here. If all of these conditions are true, then it returns true. If any one of them, or any more than one of them, or even all of them are false, then it'll return false. So this is valid coord will be a function that we're going to get to use. There's also a getNeighbors function, which we're going to have to implement. That's going to give us all of the neighbor values so that we can figure out if they're alive or dead. Because if you remember, the finite state machine operates on how many live neighbors we have. So we're also going to implement a function that's called num-alive neighbors, which is literally going to count how many alive neighbors we have. And as you can probably imagine, that's going to call this getNeighbors function, and it's going to count them. And we're also going to have this update function. So I've got paths for all of these so that we can implement this. The update function is going to execute one life time step. So it's basically going to go through every single cell in the grid, and it's going to update the state of that grid. Okay, so the main function basically looks like this. Determines the screen dimensions, it sets up the colors and so on, and then it creates this world here. And you can see that the world's made up of a lot of zeros and a few ones. And each of these, you can see that we've got like a triple of ones sideways. We've got a triple of ones vertically all over the place. And these are going to animate in a relatively basic way. And I've got a few other example starting worlds that we can use. It's going to call the draw function to draw it. It's going to update the world. We didn't do that part yet, but then it's going to draw again. So it's going to basically continue to loop. We're going to repeat a certain number of iterations. It's easier than using key presses to exit. So we'll just have it animate and then automatically quit after a certain number of characters. It's going to have then a key press, which is going to not quit the application until after we press the key. That way we can at least see the static state. Because once you quit the application, all the cursor's graphics kind of go away. All right, so let's actually start implementing some of this code. So the hardest one to implement is this getNeighbors function. The easiest one to implement is going to be, ironically, the one that we're really here for, which is the update function, which is going to do the actual finite state machine. Technically, it's the cellular automata steps. But anyway, we'll implement this getNeighbors. Just I thought this would be a fun one to do because it's relatively straightforward for us to know. All we're going to do is we're just going to go through all the surrounding states. If you can probably guess it, like if we're looking at a particular cell, then the neighbors that we care about are these ones. So we care about like this one to the right of it, this one to the left of it. We also care about the diagonal, the one directly above, diagonal to the right, diagonal to the left and down, the one directly below, and the one diagonally to the right and down. So we need basically all 8 of these steps. And this is just basically brute force. So we're just going to say get the neighbors from the row above. I'm just going to use I'm just going to call that function. So I'm just going to say if is valid coord. Pass the world to it because we're going to use the world to determine the dimensions. You can see that we're actually using, the size of the world here in this function. So I have to pass it the world. And I'm just going to check to see on the previous row, that's at y minus 1. And then we're going to check x minus 1 for the x position because x minus 1, this is y minus 1, but x the same. But this one right here, I don't know why, that's to highlight all of those. But anyway, this star right here is at x minus 1. So we're going to check that one. If it is, then what we're going to do is, I forgot to do this, I'm going to create a neighbors array. Sorry to any Americans watching this, I am Canadian, so I spell it the Canadian way. And if that's a valid coord, then I'm just going to append that to the neighbors. And I'm just going to grab the value from the world array, which if you remember, look down here, it's just a 0 or a 1. So we're just going to say world y minus 1 and then x minus 1. Okay, I like to put spaces around it for clarity, but you do what you want to do. Let's copy this 3 times because they're all on the previous row. But this one's going to be in the same x position as the current node. Like we're trying to find the neighbors of the cell that's at position x. And these, by the way, are reversed just because of how I structured this. You can see that the first row, which is what the first index is going to give us, if we say world square bracket 0, that's going to give us this entire row. Okay, so the first coordinate determines which row. So that's why I use y first here instead of x first. It makes more sense to have x first, but anyway. So the first one we're checking to see y minus 1, x minus 1. Second one we're doing y minus 1, x. And the third one we're going to do y minus 1, x plus 1. And that is because that's supposed to correspond to this corner piece here at the top right. All right. Now what we're going to do is we're going to do get the neighbors from the same row. Whoops. And I'm going to copy the code still because it's pretty easy to modify. There's going to be 2 of them. If they're on the same row, we don't say my minus 1. So let's get rid of all those minus 1s here. And we're going to pick the one that's to the left of the current element. So that's x minus 1 and x minus 1. And then the other one is to the right. That's x plus 1. Okay? And then we're also going to have the ones that are on the row below. So let's put that in too. So I'm going to copy even the comment. So I'm going to say from the row below. And these are going to be at position, the y position is going to be y plus 1. I could use some fancy multi-cursors to do this, but easy enough to do this. So this is at the row below and the left, the column to the left. So this would be the row below, same column. And this is the row below, column 1 to the right. Okay, so that's going to add all of those neighbors. Again, I'm checking as valid chords, so the number of neighbors that I get could be as many as 8, but it could also be less. Imagine if we're in the top corner doesn't have any neighbors to, so let's say we're in the top right corner, we don't have any neighbors to the right, and we also don't have any neighbors up. So this all these if statements here will fail, and also the one to the right here, and the one to the right here will also fail. Okay, so then we're just going to return the neighbors list. Oops. Okay, so there we go. There is that function. Pretty straightforward. So it's long, but it's pretty straightforward. Okay, so I like to collapse the ones that I'm not using. I don't know why it doesn't collapse the comments here. I guess they're not technically part of the function. All right, so this should be easy now because we have a function that can tell us what all the neighbors are. All I now need to do is to get how many there are. So let's first grab the neighbors. So I'm going to say get neighbors. Pass in the world, pass in the x and y position of the current cell, and then I'm just going to return neighbors.count1. This is how many alive neighbors, right? Alive is represented by 1 in the list. So if we have this list of, say, 8 neighbors, how many of them are 1s? We're just going to use the count function, which, remember, in lists is just going to return a number 0 or greater, which is how many of those elements are 1s. And we're creating a list, so we can use this list function. So there we go, num alive neighbors. All right, so now to the interesting bit. We're going to create an update function. The purpose of the update function is to create a new world variable. So I'm going to create a new variable called new world, and I'm going to set that to blank string for right now. And let's just go row by column through the world. The reason why, by the way, I'm using a brand new world as opposed to just modifying the values in the old world is because as I do that, if I, for example, modify one cell, when I go down to the next row, it's going to look up at the previous row to see what the current status is, and those are going to be the new values. And it's also going to look down to the next row, and those are going to be the old values. I don't want to mix new and old values. I want to use all the old values for determining what the new values for the cells are going to be. So that's why I'm creating a whole new array. It does a whole new list. It does actually add a little bit of complexity, but it's worth it because I'm sure that this is going to behave properly. So I'm just going to loop over all of them. Notice that I am making sure that my code will be flexible if I decide to make a larger world. The only thing is curses can't display like an infinitely really large grid because it's only how much space you have available in the console. But I'm specifically using range len of world so that if I make my world a little bit bigger, a little bit more columns or more rows, it'll still work. Okay, so for the current row, I'm going to actually create a new row array. Because remember that a two-dimensional array is really just an array, a list of lists. So a two-dimensional list is a list of lists. So I'm just going to create a list that represents the current row, and then I'm going to append that to new world when we're done. Okay, so I'm going to say for x in range, len of world. Now, len of world is how many rows we have, how many of these lists we have in the list. But I don't want that for the number of columns. For the number of columns, I want to get how many rows, how many columns we have in the current row. So that's why I'm saying the length of the world at index y. Now all of these rows have the same length because that's how I've designed it. But even if I were to make one of these rows a little bit longer, my program can still handle that without bugging out. So it's really a good idea to keep this as error-proof as you possibly can. It's just a good practice. Okay, so let's figure out how many alive neighbors we have. I'll just say num neighbors instead of num alive neighbors, just for shortness. And we'll pass in the world and the y and x coordinates to that. And notice here that I specified y and x in this order here. So let's make sure that you put it in the right order. All right, then we have 3 rules. So the rule 1 is a live cell with less than 2 alive neighbors dies. We call this underpopulation. That's that rule. Okay. Another rule, a live cell with 2 or 3 alive neighbors, it stays alive. We'll call this the survival rule. I don't think that is the official rule name, but I'm going to call it that. And if we have an alive cell that has greater than 3 alive neighbors, then that's going to be a dead cell, and this is overpopulation. That's the official name of this rule. And there's one more rule, which is rule 4. This is a dead cell with exactly 3 alive neighbors. It's alive, and this is the reproduction. Okay, so that's the rules. Very easy for us to do here. So I'm just going to have a big elif here. So I'm just going to say if world at yx is equal to 1, in other words, it's alive, and the number of neighbors is less than 2, so that corresponds exactly to this rule here, then we want the value to be 0. So we're going to say new row dot append 0. So we want to make sure that the current cell is 0 or it's dead, right? That has to do with the fact that this is dead. You know what? Actually, let's just say dead. This is like a state down here. All right, so because the next rule is pretty similar, I'm going to just, actually, they're all pretty similar. Let's just copy and paste them all. So the next one is rule 2. If we have an alive cell, so this is already alive, and we have either 2 or 3 alive neighbors. So let's put brackets around this because we're going to be combining ands and ors. And so I'm just going to say if the number of neighbors is equal to 2 or the number of neighbors is equal to 3, then I'm alive. This cell is alive. So let's append a 1. So there's rule 2. And if we're alive and we have greater than 3 alive neighbors, then we're going to be, this cell is going to be dead, so we're going to do that. And then rule 4 is if we are a dead cell, so in other words, if the value is currently a 0, and the number of neighbors is exactly 3, then we are going to be alive. This is like, you know, a newborn baby or whatever. Okay, so there's the rule. Anyway, so that's pretty straightforward. Now, the other thing is I put ifs in here. I really mean for this to be an else if. That's just because I copied and pasted. Now, these are all mutually exclusive, so that's not a really big deal. But by using elif, I can put an else at the end. That's going to do the trick for any other case. Okay, there aren't that many cases left, because if you look at the alive cells, there are 3 rules for alive cells. One of them is less than 2 neighbors, one of them is 2 or 3 neighbors, and one of them is greater than 3. So these account for all the situations for an alive cell. But this one here doesn't account for all the situations for a dead cell. And so I actually need to handle dead cells. So if I have a dead cell that has more than 3 neighbors, or it has less than 3 neighbors, there's no rule about that, and the idea is it stays dead. So we could literally say new row append 0. Okay. And then all we need to do now is just some housekeeping. At the end of the loop here, I'm just going to append the new row to the end of the new world. Okay, and at the end of the outer loop, I'm just going to return the new world. So that's going to eventually replace the old world. All right, so there is the update function. So let's go to our main function now and figure out what we're supposed to do. This is going to be the easy part, because all we have to do right here is update the world. So it says to do. So all I'm literally going to do is just say world equals update world. Okay? All right, so now let's go to our code here, and we're going to give this a run. So I'm just going to say Python 3 state machine demo. Hopefully that's the right one. And then we can see there's our oscillator. So it looks pretty neat. This particular one, you can see it's called an oscillator because it oscillates between a couple different states. You can see it just goes back and forth and back and forth, and the states kind of play off of one another. I'll quickly show you. I have to wait for the 200 steps to end. But just as an example, I can show you something really, really simple. Oh yeah, this was called a pulsar. But anyway, it's probably too complicated to change this entire thing. But one thing I could do, maybe up in the top corner here, what I'll do is I will change this to a 111, just kind of on its own here. And that actually will impact. Need a little bit more space. Okay. Yeah, let's probably, I should not be ad-libbing here, but down the bottom here, yeah, it looks like this one is far enough away that I could change this and make a triple right here. It doesn't look like it'll impact anything. So that should be almost the same. It'll still do the oscillator. But down in the bottom corner, we'll have a different oscillator. So we'll have the pulsar, the really big complicated oscillator. And then down here, this is like the simplest oscillator that just alternates between a vertical triple and a horizontal triple, which is pretty neat, I think. Okay, anyway, after 200 steps, we should end. So I'll just sort of wait for that. Yep. So what I want to show you now is another cool thing. It's called, there's 3 things actually. So I'm just going to paste them in here. They're commented out right now, so I'm just going to uncomment them. Okay, so this is actually an oscillator, which we just saw, and also a static, which is a square, and a glider, which is probably the more interesting thing. So if you look right here, you can see that there's a square of 4 ones, and according to the rules, all of these ones have 3 neighbors. You can just assume that they're all dead cells around it. They all have 3 neighbors, and since 3 neighbors means that you get to keep surviving, this square is just going to keep surviving. So that's why it's called a static. The oscillator, on the other hand, let's see if we can find it in here. Right here. So we've got the 3 in a row. I showed you this on the last one. Well, each one of these has different state. Like the one up here only has 1 neighbor, and the one down here only has 1 neighbor. So these 2 cells are going to die on the next stage. But this cell over here is currently dead, but it has it has 3 neighbors, exactly the amount that we need for the reproduction rule. So this cell is going to become alive, and this cell is going to become alive because it also has 3 neighbors. So let's watch all 3 of those in action. I'll show you the glider after. That's this shape right here, kind of like a diagonal line and then a vertical line here. That one's probably the coolest one of them all, and I'll explain it as it's animating. Okay, so let's see the static and the oscillator. The glider, as you can see, it kind of glides across the screen, which is quite neat. Eventually turns into a square when it gets to the bottom because it doesn't have enough neighbors to keep reproducing, but I still think that's quite neat. And that's just an artifact of that particular shape that causes it oscillates, but it also moves as it oscillates. So it's pretty neat. Okay. Let's do one more, and this one is probably the coolest one of all. We've seen a glider, but what about a component that generates gliders? This is called the glider gun, Gosper's glider gun. So we run this one again. This one's a little bigger, obviously, because we need a little bit more space. But let's see what that looks like. You can see we've got these 2 things that are kind of bouncing back and forth. And when they collide in the center, the shape that they produce decays to a glider. And then the glider does what gliders do. It kind of sails off the screen. So we've got things like motion, and we've got like reproduction. And hopefully you can start to see why they call this the game of life. Because you can create things that kind of mimic some of the lifelike behaviors that we see. All right, anyway, so I thought that's pretty interesting. As I said, down in the description, I'll link to where you can find out more information about how to install the curses library, but also a website where you can just kind of draw the state and see what happens. And there's a couple of cool examples that you could try out from that if you wanted to. All right, so thanks, everybody.